Continue with giving some hints about this question. Whether you do it in your quiz or not depends on you. You don't have to do it. They won't be evaluated anyway. As you see, if you remember the Fourier series representation of this x of t signal was another impulse train. You remember that? The Fourier series of this one, let's call them AKs, over the frequency axis. It may be the omega frequency axis, then everything must be multiplied by 2 pi. It was another impulse train. And these impulses were separated by the fundamental frequency. What's the fundamental frequency? If 2 milliseconds is the period, then 1 over 2 milliseconds is the fundamental frequency, which is 500 hertz. Therefore, this is 500 if this is hertz. Then this is 1000. The next one is at 1500, and it goes on like that. And what you really have to do is you have to apply the filter in a multiplicative form, and you will see that this thing, the fundamental or the DC component, will pass with an amplification factor of 1. These two will also pass with an amplification or an attenuation factor this time of 2 over 3. So whatever the magnitude of this one is, which is 2 pi over capital T, all right, if you remember from the Fourier series coefficients. So this will be multiplied by 2 over 3, and overall it will make a value. Let's call that value A for the magnitude of these two impulses. And sorry, it goes on like this to minus 1500 from minus 1500 to 1500. So the coefficient, the harmonics at frequency 100 hertz or 1 kilohertz, let's call, will also pass, but the amplification factor will be 1 over 3. If this is 1, this is 2 over 3, this is 1 over 3, and this is 0. So the harmonics at 1500 will not pass. The negative one will not pass either. And all the other further harmonics, they will not pass. So how many harmonics are passing? 1 from the DC, 2 from 500 hertz, and 2 from 1 kilohertz. And since they are symmetric, they are not amplified differently, the left hand side and the right hand side, these two will make a cosine at a frequency of 500. These two will make another cosine with a frequency of 1 kilohertz. So there will be a DC, some constant, A, let's call it, plus B times cosine something, plus C times cosine something else. This something is at 500 hertz, this something is at 1 kilohertz. In fact, the value here, which is denoted by C here, is half of B, because this one is scaled by 2 over 3, this one is scaled by 1 over 3. So this is half the magnitude of this cosine. You have to obtain something like that, okay? You should be expecting such things in examinations. What other things will you be expecting? Now I'm trying to invent some questions without much detail. For example, again, an impulse train, x of t, okay? And here we have y of t, which is some rectangular shape like this. That's possible. It's not periodic, by the way. And I say z of t is equal to x of t convolution with y of t. And I'm asking the Fourier series coefficients or the Fourier series representations of z of t. That's the question. Does it make sense? This is an impulse train, periodic. Therefore, when you convolve this rectangle with this impulse train, as you always encounter, it will produce a periodic replica of these rectangular pulses. So the overall shape will be a periodic pulse train, not an impulse train, but rectangular pulse train. And it will certainly have Fourier series coefficients. That's what you need to find then. An indirect way of asking a Fourier series kind of question. A possible question. What other possible questions are there? For example, I may ask you the Fourier series coefficients of this sawtooth shape. With a period. I don't know what it is. So how are you going to find the Fourier series coefficients of this thing then? For example, I would, instead of directly applying the integral formula for the Fourier series coefficients, what I would do is, if this is x of t, then I would take the time derivative of it and take a look at what's happening. And the time derivative is an interesting thing because everywhere except these instances of impulses, the time derivative of this thing is a constant. Whatever the slope of this angle is, that thing is this level. So what are these then? They are impulses with negative values. You may denote them like this, downward going impulses. That's a bad notation. Scientifically, it would make more sense if you could put arrows upward going and put a minus label to it, which shows a negative value. But whatever. At every period instance, it imposes a downward going infinite slope. So that is these negative things. So this is an impulse train. This portion is an impulse train. And this is a constant. So what is the overall thing? You can find the Fourier series coefficients of a constant which consists of only one harmonic, which is the DC, A0. For these, it's an impulse train, so it has normal Fourier series representation of constant Fourier series coefficient. It doesn't change. And their combination, the summation of this one and this one, will correspond to this x prime of t, which is the derivative. From the derivative, what do you need to do? You need to take the integral of this thing to have this. So the derivative of this one is this, the integral of this one is this. And there is a property relating integrals and derivatives. The Fourier series coefficients have a relation. Okay, that was property number something. And use that property, which divides the Fourier series coefficients that you find from here, from x prime of t, by 1 over jk omega 0. So whatever ak's you find from here, you divide them you would divide them by jk omega 0, and they will be the Fourier series coefficients of the top figure. So as you see, this is again an indirect way of asking questions. And you should be expecting such questions in examinations. In the first exam, I asked rather direct questions, and let me be honest about this. Such questions, this one, and this one, are also direct questions with no further puzzles or anything. They are not problems. They are solid questions. And I will go on asking solid questions. I don't want you to solve problems because I don't feel that you are able to do that. The first midterm, I haven't finished evaluating them. but the first midterm results are not very promising. And as I say, you have to be very careful about one thing. I'm not going to pass you from the course with overall grades like 30 or something, 25, 30 or something. You won't be passing. There will be nothing passing from this course if your overall average grade is below 50 at least. Okay? So I'm asking you solid and non-problem questions, and I'm expecting correct answers from you. So be very careful about answering questions. For in the first midterm, it's a little bit disappointing. Okay? So be careful about that. Oh, by the way, there was, I don't know, 20 points or 25 points. There was some bonus. 20 points. So among 120, you are losing your chances. Don't do that. I'm giving you questions, you know, and I did the same. I did the same in the first midterm as well. I said that I'm gonna ask this, I'm gonna ask that. And it is surprising that even those questions that I have already given you were not answered properly. What's the matter? Okay, don't do that. For example, I'm not gonna ask you questions like this one, which we have started in the previous hour. What was that? We have some observations of a continuous time periodic signal, and the observations were that it's real and it's periodic with period is equal to 4, and Fourier series coefficients are AKs, therefore, and it has finite Fourier series coefficients. The coefficients magnitudes are 0 for k greater than 1. So we have a minus 1, a0, and a1, only 3 Fourier series coefficients. It's a sinusoid, therefore, either a cosine or a sine or some sinusoid with a phase plus perhaps some DC offset, because there is also a0 probably. So only 3 coefficients, 2 of them will make a sinusoid and 1 will be the DC. That's what we are trying to find. And we observe an indirect y of t, which is odd, and its Fourier series coefficients are bk's, which is related with the Fourier series coefficients that you're looking for. Ak's, like this. It is e to the minus j k pi over 2. A minus k. This relation between the Fourier series coefficients is automatically indicating the relation between y of t and x of t. What are they? What's the relation between y of t and x of t if the Fourier series coefficients of y of t and the Fourier series coefficients of x of t, which are ak's, are given like this? bk is equal to e to the j something times a minus k. Without considering this e to the j something, bk is equal to a minus k corresponds to a time reversal. Okay? Cosine of t becomes cosine of minus t, for example, time reversed. This thing corresponds to that. Furthermore, with this e to the j k pi over 2 thing, it corresponds to the shift, as you have suggested. Okay? So it is a flipped around and shifted version of the original x of t. That is y of t. And we say that when you flip around x of t and shift, the signal that you obtain as y of t is odd. Now what is that? If something is odd, if some signal is odd, can it have a DC coefficient? That's the first observation that you start making. An odd signal can never have a DC coefficient because it says y of t is equal to minus y of minus t. That is an odd signal. For example, a sine is an odd signal. Sorry. And it goes on, of course. Like this. This is an odd signal. This value at minus t is the negative of this value at plus t. So this value is the negative of this value. For an antisymmetry like this, you cannot have a DC coefficient. For a symmetric sequence, you can have a DC. For instance, this is a cosine plus some DC. And it's a symmetric sequence because, as you see, this value is the same as this value. This value is the same as this value. So it is symmetric. And there may be a DC coefficient. That is possible. But for an antisymmetric, an odd signal, you cannot have a DC. Which says that B0 is equal to 0 immediately. And notice this equation. If B0 is 0, then it is a complex exponential times A0, which means A0 is also 0. In other words, our x of t that we are looking for has no DC. It shouldn't have any DC because we know that when you flip it around and shift, the signal that you contain is odd, which means there is no DC of that. Then the original non-flipped around and non-shifted version, which is x of t, shouldn't have any DC either. That's how you conclude. So A0 is equal to 0. The first observation or the first result that we conclude from these observations. So there are only two terms that we're looking for, A1 and A minus 1, because originally there were only 3 from the third item. And we said that DC is also 0. So that's what we need. What other observations do we have? The fifth and the last observation is the energy. This is equal to 1 over 2. So the power of the signal is 1 over 2. That is the power of the signal in time domain. And from Parsev's theorem, we know that that power is automatically equal to the summation of the magnitude squared versions of the Fourier series coefficients. So A1 square plus A minus 1 square is equal to 1 over 2. And since it's a sinusoid that we're looking for, from conjugate symmetry, because it's a real signal, if what we're looking for is a real signal, then A1 and A minus 1 must be conjugate symmetric. They can be equal if it's a cosine. They can be negatives of each other if it's a sine, but otherwise we know that A1 is A minus 1's conjugate. So they have the same magnitude in short. What I'm saying is 2 times A1 square is equal to 1 over 2, which makes A1 square is equal to 1 over 4, which makes the absolute value or the magnitude of A1, which is the same as the magnitude of A minus 1, is equal to 1 over 2. So how did we proceed? We first said that there are only 2 Fourier series coefficients because A0 is 0. It's only A1 and A minus 1. And their magnitudes are equal to 1 over 2. Now, if y of t is odd from here, we say that b1 and b minus 1 must consist of only imaginary parts, because for a real and odd signal, the Fourier series coefficients are purely imaginary. For a real and symmetric, they are purely real. A cosine, for example, what are the Fourier series coefficients of a cosine? 1 over 2. What are the Fourier series coefficients of a sine? 1 over 2j. So they are purely imaginary, as you see. The same argument holds here. Y of t is odd, which means the Fourier series coefficients of this thing must consist of purely imaginary numbers, like plus and minus. So b1 is equal to plus or minus 1 over 2j, which is the same as saying j over 2, whatever. But we don't know whether it's a plus j over 2 or minus j over 2. If it is plus j over 2, then b minus 1 is minus j over 2, the negative of the other one, the conjugate symmetric version. So b minus 1 is this time minus or plus j over 2. Whatever the sign of this thing, the sign of the other one is just the inverse of it. And if we continue from here, sorry for the blackboard usage, a1 is equal to e to the minus j pi over 2, and k is 1 here. I'm using this relation between bk and a minus k. So it is, sorry, this is plus. a1 then is equal to e to the plus j pi over 2 b minus 1. And conversely, a minus 1 is equal to e to the j pi over 2 with a minus sign b1. And a1 and b1 are either j over 2 or minus j over 2. So we don't know the sign. We couldn't find the sign of it. This e to the j pi over 2 thing corresponds to a plus 1. A plus j. Or a minus j for the other one. So that's equal to j, and when you multiply plus or minus j over 2 by j, what does it become? Plus or minus 1 over 2 it becomes. So a1 is equal to plus or minus 1 over 2, and a minus 1 is also the same sign value of plus or minus 1 over 2. If this is plus 1 over 2, this is also plus 1 over 2. If this is minus 1 over 2, this one is also minus 1 over 2. So that's what we conclude from these expressions of a1 and a minus 1. Since the sign of the other one changes with a minus j here, because it becomes 1 over j, so it makes a minus j. The minus j multiplies the minus, the plus j multiplies the plus j. So the signs of a1 and a minus 1 become the same. But we don't know whether they are both positive or they are both negative. So what is the conclusion then? The question is asking me, what is the signal x of t? And my answer to that is it's either plus cosine or a minus cosine pi t over 2, or 2 pi over 4t, because the period is 4 from the origin. So this is x of t of your question. you could say that, well, we couldn't find the exact solution. It's either plus or minus. But with these 5 observations only, from 1 to 5, this is as much as you can get. And you must leave the result like this. Plus or minus cosine pi t over 2. Now this is, as you see, a problem question. And it's not asking the Fourier series coefficients. It's not asking the output of a filter or anything. It's just asking to derive a signal, x of t, from these observations. There are some other questions resembling this one. There are some other questions involving even more complicated things, including problems from real life, in the Oppenheim's book. So please take a look at the questions. Okay, you will always encounter such things. Maybe not in the examinations, but in real life, such questions are possible. Yeah.
Why is it called SJ?
Here, e to the j pi over 2.
Why is it called that J?
Because it is. It is cosine pi over 2 plus j sine pi over 2. Okay? And cosine pi over 2 is 0, sine pi over 2 is 1. You can always think of the value, the imaginary and the real values of complex exponentials from the complex circle. Okay? If the angle is 0, you are here. If it goes on like this, this is pi, and then it rotates again and it goes to 2 pi. So one whole circle is 2 pi. This is the real axis and this is the imaginary, or the j-axis. And this is the angle that you have, for example. For example, this angle. That's the theta. So what is e to the j theta? E to the j theta is cosine is this much and sine is this much. So this much real value and this much imaginary value comes into the picture. And this is pi, therefore this is pi over 2. When it comes to 90 degrees, which is pi over 2, the real part is nothing, 0, and the imaginary part is as much as the radius of this circle, which is unity, 1. If it goes further, then it becomes minus 1 at angle equals pi. Then it will become minus j for angle minus pi over 2. By the way, 3 pi over 2 is equal to minus pi over 2 if you go in the other way. All right? Always think of this complex circle as an evaluation tool for e to the j theta, if theta is known, and here it is pi over 2. All right, so much about the Fourier series coefficients of continuous time periodic signals. Now we will make a start to the Fourier series representation of discrete time periodic signal. Previously it was continuous time periodic signals. Now we have discrete time periodic signals. The concept of a periodic signal in discrete time was a little bit different, if you may remember. We were saying that x of n must be equal to x of n plus capital N for some capital N element of an integer. Therefore, the period of a periodic discrete time signal must be integer. That's a difference between this one and the continuous time case. That is one difference. One other difference is this. If the period is capital N, then the fundamental frequency that we're talking about is 2 pi over capital N. Okay, another or one natural observation. We know that the Fourier series coefficients, AKs, are related with the corresponding frequency. What was the frequency of AK? The kth harmonic. That was k times omega 0. You remember that? And omega 0 is equal to 2 pi over capital N times k. Now some unexpectedly expected thing is happening here. This capital N is an integer and this k is also an integer. Okay? What happens, for instance, when k is equal to exactly capital N? Let's give an example like this. Example, capital N is equal to 10. What do you say about AK or A10, in other words, is equal to what? Or what is the corresponding frequency of A10? I'm putting a tilde for the association of frequency of this 10th harmonic. What's the frequency of that? It is equal to 2 pi over N times, which is 10, times 10, that is equal to 2 pi. Now what does 2 pi mean in discrete frequency? 2 pi, consider the same circle here, truly corresponds to the zero frequency. A complex exponential with frequency 2 pi is the same as a complex exponential with the frequency 0. Because e to the j 2 pi is equal to 1 as well as e to the j 0 is equal to 1. So 2 pi is DC. Again. Now what does this say? It says that if your discrete time periodic signal has a period 10, then the 10th Fourier series coefficient's frequency is the same as the DC frequency, which means that A10 is nothing but A0. It's the same. It goes back to A0. That is the fundamental difference between the continuous time case and the discrete time case. In the discrete case, the Fourier series coefficients start repeating themselves after some time, after the number of items equal to the period. The period is 10, then there are only 10 distinct Fourier series coefficients from A0 to A9, and then A10 is the same as A0. A11 is the same as A1. A12 is the same as A2. It goes on like this. In the negative axis, it repeats itself similarly. So there are only capital N distinct Fourier series coefficients. No more than that. Only capital N distinct Fourier series coefficients. That is the first thing that you must have. That was not the same for continuous time periodic signals, because we know that they may go to infinity. They usually decay. They usually decay in magnitude. Or for impulse trains, they don't even decay. But now that's not true. We have only n. For example, let's assume n is equal to 5. Then this is A0. Then this is A1. This is A2. This is A3. And this is A4. Take this, and then it repeats itself to the left, to the right, everywhere. 5, Fourier series coefficients. And this thing, which is, let's call it A5, is the same as A0. And the frequency axis is quite easy as well. Normally you should put the corresponding fundamental frequency here, and you have to evaluate it, but let me give you a quick way of finding the frequencies here. If this is the omega axis, this first repeating thing, which is A5, happens at 2 pi. Okay? So what is this? It is 2 pi over 5. This is 4 pi over 5. This is 6 pi over 5. This is 8 pi over 5. This is 10 pi over 5, which is 2 pi. All right? So the frequencies are going on like this, and it's not very complicated to find the period here in the discrete time Fourier series representation. This gives us a strong hint about something else. It is saying that 2 pi is the same as dc, and k times 2 pi is the same as dc as well. 4 pi, in other words, is the same. 6 pi minus 2 pi. Any integer multiple of 2 pi is equal to dc. If you're having a dc, then how can you associate the corresponding filters then? For example, in continuous time, in the quiz question, I gave you this shape. And I said, this is 1500 hertz, this is minus 1500 hertz. Which is the frequency. So I gave you the filter like this. What is the DC here? DC is 0 frequency. What is the highest frequency? The highest frequency is infinity. Here or here. But on this new frequency axis, we have a problem. After some time, we are hitting back DC at 4 pi, at 6 pi. So what is the highest frequency in discrete time then? Question is this: what is the highest frequency in discrete time? The lowest frequency in discrete time is 0, but it is also 2 pi, and it's also 4 pi, etc. So what is the highest frequency then?
Pi.
Yes. That is equal to pi. Or it is equivalent to 2k plus 1 pi. All odd multiples of pi. For example, pi itself. Or 3 pi, 5 pi, minus pi, minus 3 pi, minus 7 pi. They are all corresponding to the highest frequency. And there is nothing with higher frequency than that. You can think of the situation like this. In discrete time, or in continuous time, you can draw an arbitrarily high frequency signal like this. Right? A sinusoid with an infinitely high frequency, arbitrarily high frequency. These may become as close as possible towards each other. The frequency of this thing may go to infinity. That's possible. But in discrete time, this is the axis of integer. Can you draw me the highest frequency signal? Let me do it. I can do that. The highest frequency signal that you can have is this. And there is no other signal which has higher frequency than this one. They can never become closer to each other. They must be separated by 1. Integer indices. So this is the highest frequency signal, and the frequency of this highest frequency is pi. Let's call it a sinusoid with frequency pi. I strongly recommend that you try to make this sinusoid, squeeze it 3 times. Okay, increase the frequency, which was originally pi, to 3 pi. Increase it to 3 pi, and make the sampling at exactly the same integer values. You will see that it is positive, negative, positive, negative, positive, negative again. In fact, if you increase the period frequency of the sinusoid to twice and make it 2 pi, when you make the sampling at integers 0, 1, 2, 3, etc., you will find the same values. The samples will correspond to the same places. And it means that it will become a DC, a constant signal. So 2 pi corresponds to a 0 frequency, and 3 pi corresponds to the highest frequency, which was pi. That is a concept of sampling of a sinusoid at integers, at integer intervals. I'm sure in high schools, physics experiments at least, you must have done a stroboscoping or a strobing experiment. Have you done it? Did you do anything like that? If something is rotating, that's a sinusoid. And when you make a sample at exactly the same places, the wheel that is rotating looks as if it has frozen. It's not moving. Okay? That corresponds to the frequency of 2 pi. In other words, the sampling frequency and the rotation frequencies are the same. That sampling makes as if the wheel is not rotating. The highest rotating amount is captured when this place is at the top sampled and bottom sampled and top sampled and bottom sampled again. That corresponds to the highest frequency in discrete time. That sampling phenomenon has an analogy between the high frequency in discrete time and the high frequency in continuous time. The wheel is rotating continuously, but your stroboscope is capturing it to produce discrete frame samples. That is also a problem in video processing as well. In the old days, the cowboy movies were captured without considering these effects. Therefore, in most of those films, when the cottage or the carriage is moving and the wheel is rotating, sometimes the wheel doesn't move, okay, in the video. That corresponds to the DC equivalence of 2 pi, effectively. Now, because of that, the filter that we are considering, I'll give you 10 to 15 minutes of break, so don't worry about that. We started late, we will stop. Don't worry about that. The filter for the discrete time case doesn't have this kind of a shape. It shouldn't have this kind of a shape in filtering purposes. In other words, I want you to filter these things again. I will ask such questions, but the filters corresponding to this one will not be like the filters in continuous time. They will be different. They will be 2 pi periodic shapes. The only difference is that. This is a normal filter, a low-pass filter. A low-pass filter in discrete time will be this. At 2 pi it's repeating, at 4 pi, at minus 2 pi, they must be repeating themselves like this. Okay, we will encounter such questions. What other things we will encounter? We will encounter questions regarding the evaluation of these 5 Fourier series coefficients, of course. The formula we haven't seen yet, but in the next hour, starting with the next hour, we will see the formula for the discrete time Fourier series coefficient. So let's give a 15 minutes of break.